Starbursts. Stars evolve because gravity always causes an unburned core to collapse and heat up. Compression stops either by the pressure of electrons touching each other or when the star enters a new phase of fusion. In this way, most of the stars continue to shine for days and years. On the other hand, some stars surprise us by showing remarkable changes in short time intervals. Supernovas are very energetic. A supernova flashes billions of times larger than the Sun, and it reaches this luminosity within a few hours of the explosion. Within a few months of a supernova's flare and extinction, the total consumption of its emanations means roughly the Sun's 10-year prime target emissivity. A low-mass star will never be hot enough to burn off the carbon in its core. Such a star becomes a white dwarf at the end of its life. At the core of a massive star, as the core continues to collapse and the temperature inside rises, fusing not only of hydrogen and helium, but also of carbon, oxygen, and even heavy elements takes place. This process continues at an accelerated rate, and after a point it reaches an unstoppable and uncontrollable point for the star. However, by the time it reaches this point, many massive stars form heavier elements, up to and including iron. When the inner core of such a massive star begins to turn into iron, alarm bells begin to ring for this star. This is because iron is the most stable element known. It does not enter into fusion reactions that will form heavier elements, and it cannot easily transform into lighter elements. In short, it functions as a fire extinguisher. That is, it ends all nuclear fires. Now the star has literally lost its skeleton. Eventually, the gravitational pull, which never ceases to attract, will overcome the pressure of the hot gas and the star will collapse into itself. At the resulting enormous temperatures, the center of the star would decompose into its electrons, neutrons, and protons, all together compressed to high densities of the order of 10 to the 18 kilograms per cubic meter. These densities are around 1 billion times the density of water, in fact comparable to the density of the atomic nucleus. This collapse lasts until the subatomic particles are squeezed together, so to speak, and become more incompressible. The collapse stops abruptly as if a hard wall has been hit, and the center backfires.